So our function is do I have this right? Tan x plus y? And we want to get the gradient at 0, 1. Do I have the problem right? So partial with respect to x. Partial with respect to x. So we have
1 over 2 times.
Right. We have square root of a function of x. So it'll be 1 over, you said, 2 times?
2 times the square root of tangent x plus y.
Right. And that's it, right?
Times secant squared.
Chain rule times the derivative of the inside. So there's partial with respect to x. What about y?
It's the same thing minus the secant squared edges.
Yeah, same thing, but this will be the derivative with respect to y inside. And that shall just be 1. So it'll be 1 over 22 times 1 this time, right? So it's the same square root of a function of y. So then you do 1 over 2 radical, and then times the derivative of the interior, which is 1. And then, so the gradient is a function. It's a vector, but there's a vector. It's a vector function, right? We've done vector functions, and so as you move around different x and y ordered pairs, you get different vectors for the gradient. So they want the particular vector that you get when x and y is 0, 1. So f of x will be, so x is 0. Tangent of 0 is? 0, right? Sine over cosine will be 0. And secant squared of 0 is? That's 1, right? Because cosine, this is 1 over cosine, so it's going to be 1. So we're going to get, and then y is 1, so it looks like I'm going to get 1/2. 1 over 2 times square root of 0 plus 1 times 1 is 1/2. Yeah, Kyle.
Why do you make it 1 over 2 tangent? Why not just make the whole thing to the 1/2 power and then do a power rule so it becomes like 1/2 times parentheses tangent x plus y raised to the negative 1/2 power?
Because it's the same thing. Yeah, so this 1/2 in the positive 1/2 in the denominator is the same as negative 1/2. So it's just a different way to do it. So that's absolutely fine to do it that way. Okay, and then the other one is also 1/2. So the gradient is 1/2, 1/2. So now, what does that mean? A new question. This is not, they didn't ask this question, but so for this surface, right? For this surface of this function at 0, 1, what does this tell us about what's going on with the surface at the point 1/2, 1/2? Or I'm sorry, at the point 0, 1, what does the vector 1/2, 1/2 tell us about this surface at 0, 1? What is that? But surfaces don't go in a direction. What do you mean?
The rate of change.
What about the rate of change of the surface?
Positive.
So this is this meaning of the gradient that we were talking about at the end of class last time. This is gradient vector. What is how steep? Is this vector how steep it is?
No.
What's that?
The surface.
Okay, what about the surface? Okay, so we got to review that. So it was kind of at the end, and thinks we had our sights on the clock, maybe. And speaking of that, so it seems that some of you have no difficulty, kind of walking out of class while I'm still talking. That's okay. If we want to run class that way, that means that I would start class right at 1:40 and would mark you late if you come in after 1:40. So we can be relaxed on both ends, or we can be strict on both ends. What do you guys vote for? Relaxed. So if I'm still talking at 3:44:30, and then still talking at 3:44:55, can you stay and listen to me finish my sentence? Is that cool? All right, instead of packing up, maybe we'll go at like, if we start a minute late some days and we go a minute late some days, would that be okay? Cool. All right. And then like in office hours, if you're talking to me, I'll never pack up my bags and walk away in office hours, okay? Yes, sir. Couldn't find what? Did anyone have trouble finding the homework?
It was due late.
Yeah, so I will make mistakes. I posted it. I guess I made it wrong for the wrong due date. So if something's wrong, if something is not in the regular cycle of things, let me know right away. And maybe some of you did. Did you email me that?
I didn't find that out until
Yeah. So it was due at 1:40 today, and if it says late, that'll be okay. That's no problem at all. But if something seems out of the ordinary, try to contact me. I'll do my best to check this inbox. Does that answer the question, David? Yeah, if it says late for this one, that won't be counted against you because I messed up when I posted it. But if you think I made a mistake, don't hesitate to reach out so I can get it corrected. Okay? All right, so gradient vector. So the gradient vector is, so here's the point 0, 1, right here. And so we've got this surface, right? And so what was the directional derivative about? It was that we could choose any direction we want, and that's horizontal, right? That's an R2 vector, an X and a Y, an R2 vector like this. We could go any direction. And then the directional derivative told us what? What was the value of the directional derivative? So say I choose this direction right here. Then and I do the directional derivative for that chosen direction, what will that value mean? What will that give me? What's that?
Well, you know the direction you're going in, so.
Yep, so I'm gonna go in this direction right here. That's my unit vector, and then I'm asking and then the book I use this notation. I used a different notation in the book, so let's figure that out. So I use this notation. The book uses this. Okay, so when the book says f sub u, that's what I call this, and this is the directional derivative. So what is the value of the directional derivative? What is it? Chandler? Or Brad?
That's the rate of change in the direction of u.
Well said, right? So it's the rate of change of f in the direction of u. So that means like how much z changes for a change horizontally in the direction of u. So that's what that value means. It means it's the rate of change. So we focused on two particular rates of change. Which two particular rates of change did we focus on? X direction, we call that the partial with respect to x. So that's this direction. And then y direction. But then we said last class, we could take combinations of changes in x and y, and that determines a direction other than the x and y direction. And then we can find the rate of change in that particular direction. So it's kind of like if you're standing on the side of a mountain and you turn a 360, the steepness that you encounter will be dependent on which way you're facing, right? And as soon as you move a little bit, the steepness will change. So the steepness of the mountain is like the directional derivative, the rate of change. Right? So it's like the steepness could be like this and then like this. Right? So as soon as I change my direction a little bit, I have a different rate of change. So that rate of change in the direction that you choose, that's the value of the directional derivative. Okay, and so then we said we're interested in a special rate of change. Which rate of change is special? The biggest one, right? So that we want to know like which if I'm on the side of the mountain, which way should I step? So it would be the steepest step that I could make. That'd be the greatest rate of change. And then we did the math for that, and we found out what was the direction of the greatest rate of change. Do you remember? Which u, how should I pick u?
Oh.
Yeah.
Don't you just find like direct, like an I and J, and take the coefficients, and then do a unit vector from that?
Well, so that would be for any direction, right? So I'm asking, well, how should I pick u so it's in the direction of the greatest rate of change? We figured this out.
So one that points.
Oh.
Okay, so
Increasing the most.
It's
right. So which u? So u is horizontal, right? The u is a horizontal vector that determines, like, again, I'm on the side of the mountain. So the u is a horizontal vector that's about like which direction I want to measure the rate of change of the mountain, right? The change in z for a change in that direction u. So what we said was we did the math and we said that what's that?
Gradient vector.
Gradient vector was the direction of max rate of change. Okay, so for this particular situation, it seems like you're focused on a calculation a little bit too much. I'm not talking about calculation. So it's just which direction will give me greatest rate of change. Which direction? And it turns out that the gradient vector gives you the direction of max rate of change of z, or of the surface.
what we talked about last time.
That was at the end of class. Yeah. Okay. So what is we at the point 0, 1 right here on the y-axis, we calculated the gradient to be 1/2, 1/2. So what does that mean?
That's the direction of the max rate of change.
Right. So if you make a change in, if you're changing, so this is really a change in x and a change in y that are equal, right? If you're going in the direction of equal change in x or change in y, or what angle would that be?
45.
Pi over 4. Or 45, yeah. So this is the angle pi over 4, where changes in x and y are equal to each other, 1/2, 1/2. That would be the direction you would go, so that on that surface you'd have max change in z per whatever distance you go in that direction. That's the max rate of change. Now, what is that? So then we said, so the direction of the gradient is the direction of max rate of change. And what is the rate of change? Do you remember this? What rate of change do you get as the biggest possible rate of change? Remember how to do that? The magnitude of the gradient. So this max rate of change is all about the gradient. It tells you the direction of the direction of greatest rate of change, and then the magnitude of that vector is the max rate of change. So what would it be for this one? We're going to take square root, is that square root of 1/2? Or radical 2 over 2. So for this particular function, square root of tangent x plus y, at the point 0, 1, if that were if that was a slope on the side of a mountain, then you would walk in the direction of pi over 4, or 1/2, 1/2, or 1, 1, whatever you want to call it. And the rate of change that you would encounter would be radical 2 over 2, and that's the biggest possible rate of change of all directions that you could pick. Is that better? Is that making sense? Please, David. What's that? Right, the gradient is a function, right? So the gradient vector is a function of your location. It's a function of x and y. As soon as you move to a different x and y, you might get a different gradient vector. That means a different direction and a different max rate. Yeah, because the gradient is a function of where you are. Plug in a different point, new gradient vector, so new direction of max rate of change, and new max rate of change.
The magnitude is just the max rate of change of that gradient vector.
So yeah, so it's, say it again?
So like that's the gradient vector, and you're saying the max rate of change is the magnitude of that.
Yep.
Okay.
The magnitude of the gradient.
Is the max rate of change.
Right. So we'll go through the slide fast again where that came from, and then it'll be like, oh, okay. But so we got the facts down, but then we'll quickly go through like how we derive that again. That would be good to do. Questions on number 22? Okay, I think the next one was 25. Is that right? $25. Okay, so now they're asking about what's the direction of the gradient. 34, 58, 34, 54, 58, 62. Okay. So this is 25. Am I right? 25 is the next one? Yeah. So then, get things like this. So now, given that discussion that we just had, this problem might be a little bit, make a little more sense. Do I have it right? And then we're at this point on 58, was it? Okay. And now they want the direction of the gradient. So what do these numbers mean again? Z values, right? Z values. And what was the direction of the gradient again? So what we just talked about? Direction of? Greatest rate of change. So you're standing at this point on here at z equals 58. Which way, based on the z lines, which way should you walk? Well, okay, so kind of forget about perpendicular, but just which way would you walk so that your z would go up the fastest? You'd walk towards what? 62. So would you walk towards 62 like on an angle, or would you walk straight at it? Yeah, you're going to walk straight at it, right? So you want to get to that 62 line as quick as you can. And to get to that 62 line as quick as you can, you leave perpendicular to the 58 line, right? If you go on a little bit of an angle, then it's going to take more to get to the 62. It'll be a lower rate of change. But if you go straight off the 58 towards the 62 perpendicular, then that's the direction of the gradient. So then was one of the choices like radical 2 over 2, radical 2 over 2?
They were just i's and j's, so just I plus j.
Which is 1, 1, right? So 1, 1 is I plus j. So Lena, does that make sense now?
Yeah.
Yeah, so you're gonna walk towards if you want the direction of greatest rate of change or the direction of the gradient, you're gonna walk towards the next higher line in the direction that gets you there the fastest, or with the least steps, right? So that's gonna be perpendicular to the line that you're on. Okay, next one. 30?
So it's just like with that section of questions.
Yeah.
30 is one of them. Mainly like 31 and 32. Like the ones with like I and J.
Okay.
Just didn't really understand how to like process that.
So is 30 your preference? Or
I just put that one down. I'd say probably 32.
32?
Yeah.
So now you go in that direction from 0, -2. That's on the negative y-axis. You're going to go in the direction what? So 1 minus 2.
Okay.
And then you just say, is your z going up or down in that direction? Is that better?
Yeah, that makes sense.
Let's do it. Let's go ahead and do it anyway. So at 0, -2, I think we got circles like this. And as you get closer to the origin, do the z's get bigger or smaller?
Smaller.
Smaller toward the origin. Okay, and we're at 0, -2, so something like this. And so then I minus 2j.
Yeah.
So I minus 2j means the same as, oh, shoot. This is not, that what I wrote was not good. That's better. Okay, equals 1 minus 2. There we go. All right, so that means, for every change in x, we go twice as much down. So that's going to be in this direction. So if you told me that this, yeah, the circle's getting higher z values this way, then your rate of change will be positive. So what direction will be the max rate of change? Straight down, right? It'll be straight down, perpendicular to the circles. Will give you max rate of change. Okay, which direction will give you the max negative rate? Straight up. Will be always exactly the opposite direction of greatest positive rate. It'll always be pi, an angle of pi. So again, on the mountain, my greatest rate of change is this way. Then we have the exact equal and opposite rate of change in the exact opposite direction. So the opposite, what direction is that? That's the opposite of the gradient.
So the gradient's always positive. The greatest rate of change is always positive.
The greatest rate of change, the direction of the gradient, will always be the direction of greatest positive rate of change.
Okay.
Z increasing. Yep, and then if you take the opposite of both the components, you get the exact opposite direction, greatest negative rate of change.
Okay.
Tyler.
You said that applies to when we're doing obviously surfaces, like the magnitude of the gradient is the maximum and the opposite of that is the direction.
Yeah, so a contour plot is exactly this. It's just another way to express a surface. They're both expressions of. They're both representations of the function. So they're like just a different way to draw it on the page. So yes, everything is the same, except the way that you're representing the surface. Okay. All right. What's next? 69. Or is there one in between? Lots of votes for 69. 69, okay. $69. Oh, so this is just finding directional derivative. Good. What do we need to do that? Ex tangent y, 2x squared y. Do I have the function right? Okay, and they want us to find the directional derivative. The directional derivative is this function that will give us the rate of change in any direction at any point for that function. Okay, so it's a function of where you are, the location, and it's a function of then once you're at a location, what direction you pick. And so we need the gradient vector first, right? Partial with respect to x. Partial with respect to x. So that's a constant, so it's going to be tangent y e to the x plus 4xy. Yes? Okay, and then with respect to y, e to the x times secant squared y, good, plus 2x squared. So there's our gradient. And then, so they're calling it what? F. They're calling directional derivative this. That's the way they're. Which I kind of like because it's similar to these, right? We know what this is. This is the rate of change in the x direction. This is the rate of change in the y direction. So this is the rate of change in any chosen direction, the unit vector. Okay, so I kind of like that. I've never seen that before, but I like that. Okay, so what is that? That's going to be the gradient. What? Dot. Whatever the unit vector is, right? So the directional derivative, the rate of change, is the gradient dot u, and we saw where that came from last time. It came right from. Well, it came from rate times little change in x, right? Rate, so the x rate times little change in x, that's the x component of the u vector, plus the rate of change of y times little change in the y direction. The unit vector are those changes such that we get a horizontal change of 1, and so then we get the rate of change, if you remember that discussion. So what do we want? For the first one, the unit vector is, they give us the point.
0, pi over 4.
Okay, so that's the point, the location.
And then direction I minus j.
Yeah.
So at 0, comma, pi over 4 in the direction.
I minus j.
So I minus j. So would that be 1, negative 1? Is that the unit vector? Careful. It's a vector. That's our direction, but is it a unit vector? It's got to be a unit vector, right? So what unit vector in that direction?
1 over radical 2 comma negative 1 over radical 2.
Good. So this is the unit vector. And that you have to use to get the right rate of change, you have to use a vector of magnitude 1 in the direction that you want, not just any direction vector. So then it's just a matter of plugging everything in. So 0 and pi over 4 are going to go in for x and y. So let's see if we can do that. That would be 1. That's going to be 1 plus 0. And then 1 secant squared y. It's 1 over cosine. So I think squared is 2 plus 0. Check my math. That's what I get for the gradient at 0 pi over 4. I get 1 comma 2.
Yeah.
People nodding? People are nodding? Good. All right, dot. 1 over square root of 2. Negative 1 over square root of 2. So then you do the math, do the dot product, and you get 1 over square root of 2 minus 2 over square root of 2, which is negative 1 over square root of 2. All right, what did that number what does that tell us? So who can interpret that number, negative 1 over square root of 2? What does it mean?
That's the greatest rate of change.
The greatest rate of change.
Of 1 negative 1.
Is it the greatest rate of change? Tyler? Right, so we didn't pick the direction of the gradient. We just used the direction they gave us.
Oh, okay.
So that's not necessarily the gradient. If it's not the gradient, then it's not the max rate of change.
So it's just the rate of change at that point in the direction of that.
Perfect. Right.
Okay.
So this is the rate of change of z with respect to horizontal distance in that direction at the point 0 pi over 4.
Okay, that makes sense. Is that the same thing as negative square root of 2 over 2?
Yeah. If you rationalize the denominator. Is part B just a similar exercise? Do we need to do part B also?
It's the same thing. You're just changing the u.
You just change the u?
Yeah, it's
Okay, so we got the gradient vector, so you're just going to, and is it the same point or different point?
Same point.
Yeah, so I mean, if it's the same point, then our gradient is going to be 1 comma 2, and what direction now?
1 over 2, I believe. Well, it's the magnitude of 1 squared plus radical 3 squared, which is just 1 plus 3, right? So yeah, square root of 4, so 2. So yeah, 1 over 2 and radical 3 over 2.
Is that pi over 3? Is that the direction theta equals pi over 3? Okay, this one we had in class last time, yeah. So that's the direction pi over 3. And now the rate of change will be? One half plus radical 3. Did I do the math right?
Yep.
So if you go in this direction, so you're at the point 0 pi over 4. If you go in this direction, the rate of change of z that you encounter is this. So from that same point 0 pi over 4, if you go in this direction, you'll encounter a positive rate of change. Okay, which direction should you go to get the max rate of change? Which direction from 0 pi over 4? What direction should you go to get the max rate of change? Which is? Okay, I'm hearing different things. What's the direction of max rate of change?
Oh, is it the 1, 2?
Yes, it's the gradient. Yep. So the direction that you would go, so this becomes the direction that you would choose, but as a unit vector. Okay. So let's prove that it works, right? So now I want to go in the direction. I want to go in the direction 1, 2. What unit vector is in the direction 1, 2? 1 over radical 5. So that's the unit vector in this direction. What rate of change do I get? 1 plus 4, 5 over radical 5? Okay. And what was the other way? So that's like actually using the formula to calculate the rate of change in the direction of the gradient, right? I took the gradient as a unit vector, dotted it with the gradient, and I got this rate. What was the other way we said you could get the max rate of change? Just the magnitude of the gradient, right? So what's the magnitude of the gradient? Square root of 5. Are they the same? They're the same. This is square root of 5. That's square root of 5. So we use the long formula to prove that, or not in this case, to show that the magnitude of the gradient is the max rate of change, or the rate of change that you get when you go in the direction of the gradient. Did that make sense? Did you follow that?
Yeah, that makes sense.
So we didn't need to do this. We could have just done this. But I wanted to show you that it's true, that if you actually plug it in the directional derivative formula, go in the direction of the gradient, the rate you get is the same as the magnitude of the gradient. Okay, last one. What's the last one?
72.
72. So now they give you, oh, awesome question, because this brings it all together. Stuff we've been doing in the last couple weeks, along with directional derivatives. So f of 510 is 200, 5.2 to 9.9 is 197. So f of 5.2 is 100, and,
It's 200.
thank you, and f of
5.2 on the 9.9 equals
0.9.
1.9?
9.9.
9.9.
9.9?
It's F of
510. Yeah,
No
500.
wonder.
Trying to see that.
Too much to remember. Okay, so 5.2 and 9.9.
Yeah.
That makes sense. Is what?
197.
So first question is, approximate the directional derivative at 510 in the direction of 529.2. So directional derivative is essentially what? So like what symbols could I write to kind of encapsulate what the number is? What's that?
Change in f over the distance.
Good. So it's a change in, so what is the change in f? What coordinate is that?
That'd be your z coordinate.
Z, right? It's like how much z changes per change in, so this is kind of weird to do this, but in the direct change in z per change in the direction of u. So I'll throw it in parentheses just because du vector doesn't really make sense, but that's the idea, right? So whenever we've been using the dot product to calculate these directional derivatives, this is the kind of value that we've been figuring out, the rate of change of z with respect to horizontal change in u. So now we have a different way to get there, right? So what is my change in z?
-3.
Right, so change in z is -3. So now, for a change of -3, how do I figure out how far I've gone in the direction of u?
You just take the magnitude.
How far have I gone? So how far I've gone in u means a combination of changes, right? It means a combination of change in x and a change in y. How much change in x do I have?
0.2.
Positive 0.2. What about change in y? Negative 0.1. So how would you figure out what your overall change was?
0.2 squared plus -0.1 squared.
Right. So you can think of that. You can think of this like a vector, and you're by saying how far you've gone, you're saying that, like the magnitude of this vector. Does that make sense to everyone? So this is the vector like in the xy plane that takes you from 510 to 5.2, 9.9. So if we want to know how far that is, that would be the magnitude of this. 0.04 plus 0.01, square root of 0.05. So let's get a decimal approximation for that.
13, well, negative 13, yeah, negative 13.42.
Okay, so do you see this is a totally different way of coming at directional derivative now? We knew what the change in z was for a change horizontally, so then we set it up as dz per, so negative 13.42. Okay, what's the next question?
So the directional derivative is just a number. It's not a vector, it's just a number.
It's a rate of change, right? A rate of change is a value. That's why when you do the dot product, you just get a scalar, right? And the directional derivative is a dot product.
Okay.
Absolutely right. Yep.
And if it says approximate f of q at point q, that is distance 0.1 from 510 in the direction of 5.2, 9.9.
Okay, so now we're at 510 and we're going
In that direction.
in this direction still? So we're still going towards this one.
Yeah.
And how far are we going?
0.1. Multiply that.
Tell me, Cutter, what now?
So if you have that directional derivative, you
Uh-huh.
multiply that by the 0.1. Now that.
Yeah, so this goes right back to our, when we were working a week ago on meanings for rate of change. There's a rate of change. What's the meaning of that rate of change? Given
A small change in x.
small change in,
X and y.
well, we got to be more specific than just x and y. Right? Given a small change in what direction?
In direction of q. 0.2 negative 1.
This, right? So this value of the directional derivative was based on going in this specific direction. So now it means that given any change in that direction,
The rate at which z is changing.
no, that is the rate at which z is changing. So given any change, or any small change in direction, 0.2, negative 0.1, the resulting, what? Not rate, but the resulting not z value. I remember we worked hard on this about a week ago, remember? Change in z, the resulting change in z will be,
Negative 13.14.
someone was saying it in the back, negative 13.42, is that the change in z? Times the change that you picked. Right? It's the same thing. It's just now we're instead of being in the x direction or in the y direction, it's just some other direction, right? So given any change in our independent, which is now a change in this direction, the resulting change in z will be that times as much as the change that you picked. Okay, so notice how this interpreting the meaning of our rate of change makes answering the question like falling out of bed, right? What was the question asked? It says you're going to start at 510 and you're going to go in that direction, this far distance, and then what does it ask for? The new value of z or the change in z?
The approximate fq.
The new value of z. So that's just, we're one step away. So how are we going to get the new value? So we're at 200, and we're going to go in that direction for this much distance.
Do we multiply the negative 13.42 times 0.1 and then add it to 200?
Good, yeah, because this is the change, right? This is how much change you'll get going from 510 to q. That's how much change in z you'll get going from 510 to q. And then to get the new z, we'll do, so it'll be f of 510 plus the rate times how far we go in that direction, which is 0.1. So that's going to be what? Negative 1.342 plus 200. $199.8.
198.7.
198.7.
Yeah.
Yeah, 198, right. Okay, did you catch what happened? Because this is all stuff we did before. This is all applying stuff we did a week ago or so. It's just now our rate of change isn't necessarily in the x or the y direction. We did all those problems for that. Now the rate of change is in some other direction, according to this direction right here. So once you get the rate of change, it's the same thing. Given any change along that path, in this case 0.1, your resulting change in z will be that rate times the 0.1, and that'll be your change in z. And you'll add that to the original z to get the new z at q. So does it at least feel familiar from a week ago? Because we were doing stuff like that. It's just we were always doing it in either the x direction or the y direction, right? We're doing these same kind of problems, just with partial with respect to x and partial with respect to y. It's exactly the same, and now we just have a derivative in a different direction. We have a rate of change in a different direction rather than x or y. Okay, David was first. Yes, this was given, right? The going 0.1 in that direction was given. Is that right? Yeah, that was good. Max.
No, just a little bit of clarification. So if
Yeah.
you say 0.1 horizontally, it shouldn't be 0.2 if we're looking at x.
So this is the direction for this rate of change, right? So you pick this direction and we calculate the rate of change with the directional derivative. Now they're saying that they say, go a distance of 0.1
Oh.
in that direction.
Oh.
So then we're going to multiply that by the negative 13.42 to get the change in z. Tyler.
So I understood the process and I get how we did everything. Just as far as the starting of it, when you have the directional derivative, the fu equals dz over du, where did you get that? The dz over du is where I was at that.
So that's just rate of change, right? Everything we've done with rate of change would be the change in the dependent variable, which is z, per change in independent. So like when we did partial with respect to x, that was dz dx. Or actually, right? That's the partial with respect to x. And then partial z, that's the partial with respect to y. And to estimate that, we would, like we use tables and graphs, like we were picking off changes. To estimate that partial derivative, we said it was get a dz from a table or a graph corresponding to some dx in that table or graph. And that gave an estimate for the partial with respect to x. Again, this is like a week and a half ago. And then same thing. So pick off a change in z from a graph or table, whatever you're working with. Get the corresponding change in y. That's rate of change. How much z changes per change in y. So now we're not in the x direction or the y direction. We're just in some other direction, right? Because now we got all these different directions we can pick. So now we're in this direction. So this was just a totally different given a totally different set of information. So now we're not given the function, we're not given the direction. Well, we can figure it out, but we're just given two function values at two different points. So from that, we figured out change in z, change in horizontal, and that ratio is the rate of change. Is it better? So it's, like I said before, it's just a totally different way of coming in at directional derivative. Instead of the dot product, it's kind of more the meaning of rate of change, right? Change in z over change in direction that you're going. Okay. Is it better? Yeah.
I'm not sure. There's a part C.
Yeah.
That
What is it?
asks Just ask for the coordinates now of that point.
The coordinates.
We found the 198.7 and what's the coordinates of that?
The coordinates. Okay, so this is good. So we're going what? We're going a distance of 0.1 in this direction. So this is back from exam 1. We want a vector that gives us what? A change in x and a change in y in this direction and has this magnitude, right? So everyone do this. We got to remember how to do this. Super important. We want to go in this direction, this far. What vector takes us in this direction, this far? How would you do it? So this is back to like the first or second week of class. See if you can remember how to do that.
I do have the answer. I know what you need to do. Oh,
Lucas, do you want to say how to do it?
sure. Do it up on the board. Oh, no, I'm good. So you find the unit vector,
Okay.
and then once you do that, then you multiply it by your scalar.
Right, so we want it to be parallel to this, but then the resulting magnitude to be 0.1. So when we multiply 0.1, we need to multiply 0.1 times a unit vector so that the resulting magnitude is 0.1. All right, so what's the unit vector here? So it's going to be 0.1 times?
Square root, sorry.
Point.
0.2 over the square root of
0.05.
0.05.
Here, so let me show you a much easier way to do this. Oh, didn't want that. Okay, so let me show you a much easier way to do this. Rather than work with all these decimals, if we know we want to go in this direction and this far, what vector could we use instead that'd be a lot easier?
2 negative.
Yeah, so we can just start off by changing this to 2, -1, because we know we're going to make it a unit vector anyway, right?
Mm-hmm.
So get rid of the decimals, just do 2, -1, and we know we want to go that far. So now the unit vector in that direction is
2 over 5.
radical 5.
-5, -1 over radical 5.
That's a lot nicer, right? So it's the same unit vector you'd get if you messed with the decimals, right? Because we started with the vector in the same direction. Okay, so then that vector is 0.2 over radical 5, negative 0.1 over radical 5. Now what? So we want the coordinates of Q, the new point. What do we do now?
Do 5 plus that and 10 minus 5.
Good, so here's our starting x, right? There's our starting x. And this vector is really representing the change, your change in x and change in y to get to Q. So you're going to do 5 plus 0.2 over radical 5. And that'll be the coordinates of Q. This idea of given a direction and a magnitude to write the vector in that direction with that magnitude keeps coming. Will keep coming back. So if you needed to refresh that today, that's okay. But just watch out for that. Questions? Okay, so let's pick a question for the quiz. And it was 1/2 x squared. Oh, thank you. That would be helpful. So negative 1/2 x squared minus 1/4 y squared plus 4. Yeah, it's over here. I'm just having trouble reading it. Okay, so that's what we got. And we looked at we remember last time we figured out the rate of change at pi over 3, right there. And we went through that process that we just did here, the directional derivative. We did the gradient dot u. Oh, and this is the 0.22, by the way. And we found that the gradient was, partial with respect to x is negative x and negative 1/2 y. So then at 2, 2, the gradient is negative 2, negative 1, right? So what quadrant is that direction, the gradient? What quadrant is that pointing? Towards the third quadrant. And actually you can see that I have that direction already notated right there. Let's see, it's right there. And so what is the direction of the gradient? What's the meaningful version of that? So what's our big conclusion about the direction of the gradient? It's the horizontal direction that gives you max rate of change on the surface or the contour lines, or however you're representing the surface. So this is the direction of max rate of change. Can you see that there? That plane is right in line with the direction of the gradient, negative 2, 1, negative 1. And so that's the max rate of change right there. David, do you have a question? Both of them, right? So this is two different representations of the same thing. So this vector, these are exactly the same graph. This is the contour plot for it, and then this is the surface. So, I mean, this is the normal orientation, right? Like this. So do you see that those vectors are the same? Right, this is our x coming out of the screen at us, y is to the right. So here's third quadrant, right? So this is x equals 0. I'm sorry, positive x-axis, positive y-axis. So third quadrant, so the same thing, positive x, positive y. Do you see it now? Yeah, so these two graphs are showing the exact same surface and the exact same vector, which is the gradient vector right now, negative 2, 1, negative 1. And so then what is this rate of change for this direction? What is this rate of change? Oh. So the rate of change in direction negative 2, negative 1 is? Radical 5. And how does that rate of change compared to every other rate of change? The greatest, because negative 2, negative 1 is the direction of the gradient. So that's and that you can see it in the picture, right? You can see that it's like looks like going up the hill the fastest. As soon as I change directions a little bit, that's not going up as fast. It's still going up pretty fast, but not as fast as radical 5. Same with over here. Still going up, but at a lesser rate than radical 5. Okay, and then what do we say, like looking at a contour plot, what's the direction of that then? Notice, what do we say about that over here? The direction of max rate of change is from here, and I want to, what? I want to get to the next z, higher z as fast as possible. So perpendicular, right? So that's perpendicular to the contour line. So this is direction negative 2, negative 1. So I want you to, your exercise is, so I want you to write 3 vectors. Direction of max negative rate of change. That's the first one. And then direction of 0 rate of change. And another direction of 0 rate of change. There's 2. So again, this idea of standing on the side of the mountain, there's going to be a max rate of change and a max negative rate of change, but then somewhere in between, won't there be a way to step so that I stay at the same z level? Somewhere in between max and min, there's going to be some direction that I step and I don't go up or down. That's 0 rate of change, right? 0 change in z. So can you figure out those 3 vectors based on the gradient being -2, -1? Let me rewrite that. It's not very clear.
You can scale it.
Direction. So vectors. 3 more vectors.
Gradient? Yeah.
Max, the direction of max negative rate of change, or the biggest negative rate of change.
Should be like the opposite of gradient. How would you
So a hint for this. Think about how this would relate to contour lines. What was the question? What was the question you asked, Lucas? What, Lucas?
Wouldn't you just find the tangent vector?
The what?
The unit tangent vector.
Yeah, but we don't have this as a function. We don't have this as a vector function. So rather than a tangent vector, what's the better question to ask?
Like the
If it's along here, it's tangent to this doesn't have to be perpendicular to that. So remember our little our trick. Remember our trick. Nope. It's easier than that.
we could. So we is that like the second derivative?
What's that?
Are we so to get that first? We can take the
Which one are you working on?
first vector.
Number 1, the max negative, or the first 0?
Well, the max is negative five just be the opposite. Yes.
So what would the vector be?
Gradient times
Because yeah,
2, 1. Brandon, what do you think?
So 2, 1, negative 1, and then number 0.
It's the max. It's the max.
Yeah, that actually doesn't really work in this scenario.
So what is going 0 rate of change? What does that have to do with the contour lines? Yeah, staying on the contour line for just a little bit, right? The direction of staying on the contour line, which is what direction? Tangent, right? So we'll just keep going with red. Let's do orange. So if it's along the contour line, tangent to the contour line, then how does that direction relate to these first 2? What did we say about these vectors? They are perpendicular to the contour line. So now if we're staying along the contour line, these 2 vectors have to be parallel to the contour line. But in order to find them, we're going to use these vectors to figure out what they are. So I showed you a little technique for doing this. In R2, there's a way to come up with, do you remember this?
Yes.
Right. So what vector relationship will we have if they're orthogonal?
So this is the cross product.
Right. So, David, do you have something to contribute here?
Wait, are you saying that maximum is negative?
Did the dot product figure out as a bunch of vectors, the dot product is 0 because you're not going any.
Good. Yeah, right. So let's just call this like AB or something, okay? So what do we know? Doesn't the vector -2, -1 dotted with AB have to be 0?
Yes.
But here's another trick. Look. So this is 2. The fact that this has a magnitude of 2 means, that right there is 2, right? Per that being 1. So no. Agree? So how will the components of, say, this vector compare to x of 2 and y of 1? What will the x component be? 1? They flip, right? So now, if you have orthogonal vectors in R2, what will the x component be there? Will it be 1? -1, right? So, do you see by the geometry that the y component, the magnitude of the y component here is going to be the magnitude of the x component here, and the magnitude of the x component here will be the magnitude of the y component here. So this is a little trick you can do to figure out an orthogonal vector in R2. So what? And then we can check it with the dot product, right? If we did it right, then the dot product should be 0. So what do we suspect that AB is? -2? -1, +2. Does everyone see that? Now, do the dot product. So, -2, -1, and -1, 2. Oh, no. Tell me you're going to do your calculator to do that dot product. I know you're going to do something else, right? You're doing something else. Okay, what is the dot product of these two? +2 and -2 equals 0, right? -2 times -1 is +2. -1 times +2 is -2. So 2 minus 2, 0. Got it. Then what will this one be? 1, -2. And that should also be orthogonal to both of these. So yes, you can switch the components and then figure out what the signs need to be. Just do the sign visually, right? So don't try to remember a rule about the sign, just do it visually. Like, you know that the magnitudes are going to be swapped. So you've got 2 here, so you know your y magnitude will be 2. You got magnitude 1, so you know your x magnitude will be 1. And then just visually, okay, so is this -1 or +1? Negative. Is this -2 or +2? Positive. And then the opposite for this one. Okay, so there's this relationship now. The gradient gives us more than just max rate of change. If you turn exactly around, you get max negative rate of change. And what's the magnitude of the max negative rate of change? What's the biggest negative rate of change? Square root of 5? Negative square root of 5, right? Downhill. Square root of 5 downhill. And then perpendicular to both of those, or parallel or tangent to the contour line, you have direction of 0 rate of change. And you can check those, both of those would be orthogonal to both of these, so the dot product would be 0. So let's see that. So which direction is that, we said? One more. You know I'm going to fly over, right? I got it. So right about there. Right about there is our, which one is that? Is that the -1, 2 or 1, -2? That's 1, -2, right? X is 1, y is -2. So that's this vector right here. And you can see on the surface that you've got 0 rate of change in that direction. Does that make sense? You understand what you're looking at?
Yeah.
Cool. All right, so that wraps up directional derivative. We're going to move on to a new topic. Unless you have any more questions. New, but certainly related. Okay, and then this will be the last, what we do in class today will be the last thing for the exam. Most of the homework, so there'll be a little homework on this stuff that we're about to do in the next 40 minutes. And then, but most of the homework over the weekend will be all review stuff. And then we'll spend all day Tuesday just doing problems on the board and reviewing everything for exam next Thursday. Okay? Very good. Exam is a week from today. Exam 2 is a week from today. So, like I said, most of the homework this weekend will be starting to get ready for the exam.
I feel like
Okay, so I want to go back to focusing on the partial derivatives with respect to x and y for a second here. Does that blue point show up? Not very well. Maybe red is better. Does that show up better?
make it yellow.
Yellow?
Try yellow. Or lime green, maybe. None of these colors.
I think red was the best. I can make it bigger too. Let's see. You can see that, right?
Yeah.
Okay, we'll do that. So at this, so here's this function. Let's call it something else. F is overused, so let's call this function g. And so I'm not telling you anything about what the actual function is. What happened? Did it just go into two panes? I shouldn't have done that. What happened? Why did it go into two panes? Was it all one pane before, or was it always two like that?
It was always two.
Two window panes, two graph window panes. Oh, okay, I see. All right, we can do that. That's fine. All right, so for this function g, and this point on the surface, I want you to estimate, what can you tell me about, without knowing what the function is actually, what can you tell me about the partial with respect to x and the partial with respect to y? Can you tell me anything about those at that point on the surface? Cutter said the partial with respect to y is positive. What do the rest of you think? Philip likes that? Yeah? Jake likes it? So it would probably really help you if I gave you a plane. Does that help with the partial with respect to x or the partial with respect to y?
Y.
Good, y. And do you agree with Cutter that it's positive? Yeah. Good job. All right, what about partial with respect to x then? 0?
Just like on the
So I will put the plane on. What do you think without the plane?
it looks like it's around 0, maybe negative.
Let's try a pretty blue plane.
I mean, it's negative.
Positive or 0 or negative?
Negative.
Definitely negative, right?
Yeah, I guess.
Yes. So the plane really helps, right?
Makes it more better.
Because the more you increase your x values, the z values go down.
Right. So yep. When you're analyzing partial derivatives with respect to x or y, you're always going to let x change a little bit positive, and then see what z does. So this would be negative, right? Okay. So what would, if we took this? This is a function. This part. This is all the function of location, the partial with respect to x and y. What if we took that function and took the partial derivative of it with respect to x? What would that tell us? Yes, second derivative. So we think of it as it's just a partial derivative with respect to x of this function that is the partial derivative with respect to x. So what would that be about? David wants to try? Yeah, good. So it'd be the rate of change of the rate of change. So let's flesh that out. Okay, so here's the notation for that, fxx, or the partial of fx with respect to x. And so, like David said, it reveals how the rate of change of z with respect to x, how that rate is changing with respect to x. But if you know me by now at all, you know I want to do better than that. Who said that? Who said that? What's the meaning of this? So, if it's how the rate of change of z is changing with respect to x, Jake started us off really good. Can anyone give it a shot? What is the meaning then of the second derivative with respect to x? Okay, Lucas and Jake are talking it out. You guys have an idea? Kyle?
Would it maybe be like how the partial derivative changes?
Yeah. Yeah, so that's kind of what we said there. It's how the partial derivative with respect to x changes with respect to x.
So maybe how the intensity of the partial derivative changes as you move along the surface.
Okay. So now we want to apply the meaning for rate of change that we were working on before. Chandler, you want to try?
So is it like for every small change in z, for every small change in z, it's the like change in the derivative of just the regular partial derivative.
For every small change in what? Still going to be changes in x, right? So always, whenever we're analyzing these rates of change, it's always start with a small change in the independent variable, and then you see the result to the dependent variable. That will always be the case. So you want to try it again?
So for every small change in x,
Right?
It's like the rate of change of x changing.
Right,
I'm trying
right.
to figure out how to say that
Yeah.
better.
Anyone want to give it a shot? Lena, were you gonna try?
The rate of change of the rate of change.
Right. Okay. So and then we want to apply our meaning that we learned in the last couple weeks. Max, you want to try?
Every small change in the change of x, you change the change. It's small, it's like would it be dc times c times
Okay. All right. Brandon, did you say it?
What?
Did you get it?
He said-
All right, Brandon, go for it.
Oh, for every small change of the smallest of no, for every small. I don't know what I said. Okay, you're gonna get a spot now.
So here's the deal. Before, hey, you guys, here, let me help you. Before, this was just what? What was this before?
For any small change.
No, this thing right here.
Oh, changes.
Before it was
X squared.
no before we got into second partial derivatives. This was what quantity?
That was
Z. Okay. So now all you have to do is instead of Z, it's the rate of change of Z or the partial derivative with respect to X. So does that help? So it's the same things before, but now the new Z is the partial derivative with respect to X.
So for every small change in X, the rate of change
Given a small change in X, the resulting change in what? The partial derivative. The resulting change in the partial derivative will be that?
I don't know.
No, this is the new rate of change that we're analyzing. Yeah, David. What? Not F with respect to X. This is the rate that we're trying to figure out what it is. So that's our multiplier, right? This value, this is the rate of change that we're analyzing. So that's the multiplier, right? That's the multiplier that gives us the change in the partial derivative. So anyone try the whole thing? We're getting closer?
Yeah, keep on with Given a small change.
Given a small change in X, the resulting change in the partial derivative is
d dx z dx dz.
this is the rate of change that we're analyzing now.
Oh man.
You just throw it on
This is the multiplier. This is the multiplier times the change in X. Anyone else? Giorgio, you want to try? Okay.
So, given a small change in X,
Right?
the rate change
The rate of change
is equal to fx of xy times whatever.
Were you saying this just now? FXX?
Yeah, f of x.
Yeah, pretty close. Pretty close. Anybody else want to try? Yeah.
The rate of change is equal to the rate of change with respect to X. With respect to X.
So it sounded like you just kind of just recited this equation.
Okay, sorry. Let me try to given a small change in X.
Given a small change in X,
in the small change in X.
the resulting change in
Z.
this equals the second partial derivative times the change in X. Right?
This close to the
Given any small change in X, the change in the partial derivative is that second derivative rate times whatever change in X you picked. Right, so we're analyzing this new rate of change, which is the second derivative. So there's the rate of change that we're analyzing. It's the multiplier that gives us not changes in Z, but changes in the rate. It gives us changes in the partial with respect to X by multiplying it times the change in X. Please.
Does this sound like something that's accelerating in a certain direction?
Yeah, it kind of has to do with acceleration, yeah. The second derivative is like, yeah, because we saw the second derivative has to do with acceleration. Okay, so So if the second derivative is greater than 0, what can you conclude about what's happening to the first derivative? If this is greater than 0, then what can you say about this product? It's always still greater than 0, right? So then how is this changing? This is positive, meaning that this is how is this changing? Increasing, right? So when the second derivative is greater than 0, your rate of change with respect to x is increasing. Right? If the second derivative is positive, that means little changes in your first derivative are positive, because you get positive times a positive equals a positive. And if your change in the first derivative is positive, that means that that thing is increasing. So how can partial with respect to x be increasing? There's two different ways that partial with respect to x can be increasing. So now thinking about like the slope, right? How can the slope increase? How can the slope increase? If the slope is positive, what happens if it increases? It's more positive, right? And if the slope is negative, how does it become more positive? Less negative. So if you have a negative rate of change and it's increasing, it's becoming less negative. And if you have a positive rate of change, it's more positive. So let's take a look. Watch. So this is the rate of change getting less negative. Looks like that. The rate of change getting more positive looks like this. Watch it again. So if the rate is negative and getting in positive, it's getting less negative as x increases. Or if the rate is already positive, then it's getting more positive as x increases. So in either case, the graph is turning up, right? If the rate of change is increasing, then it's turning upward. It's turning towards a greater rate of change. And that's concave up. This is how rate of change leads to concave up or concave down, right? The rate's getting less negative or more positive means that you're turning upward, and that creates a concave up shape. See, the things I never told you, right? All right, what about, let's do it again. What if the second derivative is less than 0? Second derivative is less than 0. What can you conclude about dfx? It's negative, which means fx is decreasing. Decreasing. So, two ways that the slope can decrease. If the slope is positive or the rate is positive, what does it look like to decrease? Less positive, right? Or if it's negative, more negative. So it's the same thing as before, but the other. Yeah, so if the rate of change is decreasing, that means it could be getting less positive or it could be getting more negative. But in both cases, graph turns down as x increases, turning down. I like turning down better because it relates to the fact that x is increasing in this process. It's not just this like y are sitting there. X is increasing, and what's happening? The rate of change is changing as x increases. So that's this idea of turning down, right? Turning down. Variables vary. Variables vary. Graphs are not wires on a page or wires on the board. There was a point in time when that graph was generated point by point as the variables varied together. Okay, so let's go back to our graph that we were looking at. And let's talk about the second derivative. Second derivatives. So does this plane help us with x changing or y changing? X changing. So what'd you say? The partial with respect to x was positive or negative? So that's just talking about how z changes, right? As x increases, z decreases. It's going down. But now this talks about how the rate changes. So the question is the rate here, as x increases, is the rate increasing or decreasing? Is it getting, it's negative, is it getting more negative or less negative?
More negative.
More negative. Do you see that? The rate is getting more negative. Therefore, the second derivative is less than 0 because the rate of change is getting more, decreasing, getting more negative. And there's the shape, right? There's the turning down shape. Question? But these are all, rate of change is always it's just a local phenomenon at the point. It's always what's happening right there at the point. As soon as you move away from the point, you can have a different rate of change. Yep. Always a local phenomenon. Okay, what about y? Okay, so what did we say the partial with respect to y was? Positive or negative before? Because? What's it? So you said it's increasing. Nope, it's not the rate of change that's increasing when you're talking about this. Z, just the z value, right? So if you're talking about the first derivative, all you're saying is that z is increasing or going up. So what's happening to the rate? This is what's happening to the rate. Is it increase, getting less positive, right? Getting less, so more positive, less, and less positive as you go. Therefore, right, it's turning down, right? So because the rate is decreasing. So this means that f of y is decreasing. So the first partial is what z is doing, right? If it's positive or negative, it means z is increasing or decreasing. Second partial is how the rate is increasing or decreasing. In this case, that rate is getting less positive. So it's decreasing, so the second derivative is less than 0. Does this make sense? Let's try different points. More practice. Over here. So all four derivatives. fx, fxx, fy, fyy. I got some curveballs in. So what do you guys, Caden, what do you think about partial with respect to x? He wants negative for partial with respect to x. Because? Z is going down, exactly. Z is going down. Let's take this outside, you're going down. Going down. All right, what about should we do fxx? So what about fxx? How do you want me to change this so you can see it? Which way do you want to look? Do you want a constant y plane or a constant x plane? To see fxx? Is that going to help me see fxx? Yeah, we're going to do this one now. So we're going to need this one. This is going to help us with fxx. So
There's a little bit of a curve there.
There we go. That's better. What do we think?
It's so close to zero.
Yeah, it's really
Good. Very good. Yeah. So if it's not zero, it's very close, right? Over here, what's the rate doing? Decreasing. But then over here, increasing. So somewhere in here, there's a point where, yep, it's called an inflection point. The rate for a moment there, the rate is not changing, or you have linearity, right? If you have linearity, the rate's not changing. You're staying at the same rate. And so if it's not changing, then about? So like linearity for a moment. It's called an inflection point. Linearity for a moment, it's called an inflection point. Okay, how about Y's?
It's in the middle. It's like right here.
So it's at like the smallest point.
Yeah, it's close to it. It's like on the bottom. It's at the bottom. You get to the other side.
It's a pretty good view right there to get both of them. So what do we think? Partial with respect to y is about what is doing. Like this partial is, we're looking at z values. It's kind of really not changing, right? Kind of approximately zero. Because we have in the y direction we have a local minimum, right? We got a local minimum up there. It's like a low point. Okay, that means the second derivative is zero also, right?
No.
Yes or no? Second derivative zero?
Zero.
Yeah. If you change the derivative to zero, you're gonna get zero, right?
Well, I mean, it's constant though, so.
The derivative of 0 is 0.
Okay, what is the rate doing over here? Decreasing or increasing? So it's negative and getting what? Less negative, so that is increasing. And then what about here? Positive and getting more positive, so? Increasing. So the rate is? Increasing. Increasing. What about at the bottom?
Still is
Increasing the whole way. It's increasing the whole way because it's always turning up, right? It's not increasing through here and then suddenly it's zero and then it's increasing more. The rate just keeps increasing the whole time. Getting less negative, more positive. Therefore, greater than zero. Do you remember in Calc 1, the second derivative test? Do you remember that in Calc 1?
Not really.
Okay, let me remind you. So you would take the derivative for your critical points. If you had a critical point, then to figure out whether it was a local max or a local min, you looked at the second derivative. Remember that? If the second derivative was positive, you had a local min. If the second derivative was negative, it was a local max. So it's not zero at the top or the bottom. So it's always positive through there. Getting less the rate's getting less negative, more positive, turning up the whole way. Positive.
So is the second derivative? Okay, so the second derivative is 0 at like the inflection points.
Whereas you have linearity, right? So if you have linearity, then you have second derivative is 0. But there's never linear here, right? It's always turning up. That rate is always increasing.
Doesn't every curve though have linearity? Yeah.
But it doesn't sound quite
Not y equals x squared. There's lots that don't. Y equals x squared is never linear. It has an inflection point like x cubed. That has linearity at the origin. But y equals x squared is never linear. It's always the rate is always increasing.
Now, does it get close?
What's that? No.
No? Or is it just because it's
No, because what's the rate? The rate is
it's isn't it just 1? It's
so the rate is 2x, right? The rate of change is 2x,
and then
and the second derivative is 2. So the rate of change is always increasing at a rate of 2, never 0. This class is what? So cool and awesome? Yeah, I know. All right.
That's it.
Okay, next one. Here you go. Okay, you do all four on your own. You guys talk it out. All four. With no planes. You can do it without planes.
So it is. It's negative. It's negative. Positive. So right there, it's very close. It's not close. It's
Right, so if you think about this, let's get more negative. It's on the y.
Has a good turn on it.
It looks like it starts getting increasing now. Yeah.
All right, who do we need to hear from here? Philip, tell me. Partial with respect to x.
Okay, so that is decreasing.
The partial is decreasing? So that might be true, but what can you say about just the partial with respect to x? So what is decreasing? When you said it is decreasing, what is decreasing relative to the partial with respect to x? What's that? Yeah. There we go. All right. So what did you say? What's decreasing right here? Z, right? So that means the partial with respect to x is negative, right? Negative. Okay. Lena, how about the second partial with respect to x? So now we're asking the rate of change. As x increases, what is the rate of change doing? So imagine x, so the rate is like kind of shallow up here, but then as x increases, what happens to the rate? It becomes deeper. See that? So up here, like the rate is 0, and then now what's the rate? How is the rate changing? Is it increasing or decreasing? What's that? Getting more negative. Yeah, as you go down, more negative. Therefore, second derivative is less than 0. Let's see. Brandon over here. Tell me about why. So the first partial with respect to y. Okay, so what about, how is z changing right there? Therefore, what's that?
0.
Good. Did you guys say 0? First partial with respect to y is 0. Second partial with respect to y. Cutter wants less than 0. You guys agree? Because the rate is decreasing, getting less positive or more negative. Good. That's right. And the whole way that rate is decreasing. Okay, and so then the easiest example, but that leads us into the next thing, is the very top. So this is easy. Both partial derivatives are 0. Second derivatives are both negative. Okay, so what do we got? What is this from Calc 1? Same thing as? What do we call this? Local max. What's true at a local max? fxx, fyy equals negative. Oh, sorry. I meant to write first. Equals 0. And the second derivatives are both negative, right? So this is okay. How about there? This is a crowd pleaser. What do we got, guys and gals? That's a good view. Partial with respect to x. 0. Partial with respect to y.
0.
So, local max or local min? Local min, right? Really? Local min?
No, it's.
Yes. Oh man, at least from our perspective.
It's a max, right? Oh, wait. Wait.
Whoa. Depends on your
It's both. Some of you are saying what it is. You know what it is? Saddle point. In some direction you have max, in some direction you have min. So yeah, so you see that's it looks like a saddle. It looks like you could, throw a leg on one side, leg on the other, it'd be like a seat, right? If you could sit in there. And that's kind of like the shape of a saddle. Or like a Pringle is another thing that's like. It's a Pringle point. So here's the easiest way to draw it. It's kind of like that. So in this direction, minimum, but in this direction, max. So here you'll get, like you guys said, the first partials will both be 0, but it's not a max. It's neither a max nor a min, because in one direction you can go down, and another direction you can head up. So neither a max nor a min. So, and then another thing about saddles is it doesn't have to just be one direction of minimum and one direction of maximum. So here's a cool example. You can have multiple directions of both. Where is it? So where's the saddle point?
Everywhere.
No, not everywhere. No, there's only one saddle point there.
Center.
The origin, right? The saddle point's at the origin. And there's actually 4 directions you can go to go down. So there's like 4 maximums alternating with 4 minimums.
My gosh, that
Did you just look up that equation?
No, I actually wrote that.
Have you ever heard of graph that stuff before?
So how did I come up with that? This is, so we can talk about that. This is what? What is that right there? Z equals, you know that. That's paraboloid. So do you see the paraboloid? Okay.
Kinda.
But then as you go around in a circle, right? As theta increases, what do I want? I want a cosine function. So I'm doing a cosine function. And how do I get theta? Well, theta is the arctangent of y over x. Right? If you have an x coordinate and a y coordinate, that's opposite over adjacent. So as theta goes around, this is theta. By doing cosine of 8, that makes it wavy. So it's doing a cosine curve around a paraboloid.
How many of those?
Yes, exactly. So if I crank this up, how many do you want?
13.
Yeah, sure.
Oh my gosh.
There's 13. But unfortunately, the software starts. It's too many points, too close. Yeah, it starts. That is crazy.
You know what reminds me of like a tough